So if you're like a super genius like Laplace, then you can just have this kind of cute little smirk on your face and look at a vector valued function and just stare at it for a little bit until the answer comes to you. I'd like to do a few examples of finding potential functions. Sometimes we'll casually think of this as a kind of anti-gradient process. You're given a vector valued function and you're trying to recover what the scalar valued function was. Sometimes it's easier just to start with some scalar functions and calculate their gradients just so we can have it fresh in our mind how this process works. I'm taking each of the partial derivatives. The x partial derivative goes in the first coordinate, and then the y partial derivative, and then the z partial derivative. Observe that if you have a function that has all three variables in it, then in each coordinate, you should be looking for some kind of derivative of that variable. So because there was just an x and y to the power of 1, then in the first two coordinates, there's going to be missing an x and missing a y. And then in the last coordinate, we're going to have a 2 that comes from the z squared. Okay, here is a vector valued function that is of a very similar form to the example in part A. And I'm just going to leave it up on the screen for a second, and I just kind of want you to stare at it and see if you can observe the pattern and try to predict what I had in my mind for the scalar valued function. Oh, why did I write this so small? What is this, a math example for ants? Oftentimes, problems involving potential functions have some kind of symmetry in them where the x and the y and the z terms all follow a common pattern. The vector valued function looks very symmetric to me because I can very clearly see the chain rule happening in the numerator. Each time I take the derivative of the logarithm, I put 1 over something, and then I have to multiply by the partial derivative of the object on the inside. So that's where I'm seeing this 2x, 2y, 2z. All looks like a bunch of chain rules to me. Okay, I'm going to give this one away. What I was thinking of here was x cubed y z to the 4th. Okay, so I've thought of another example that's similar to part B, but now we're going in the reverse direction. So I'm giving you a vector valued function, and you're going to try to recover what the scalar valued function was. Hopefully you can see a lot of symmetry going on in this problem. So try to think to yourself, what kind of function could you have? And then when you took the derivative of that function, you're going to end up with like over the square root of something. Okay, did you figure it out? What I was thinking of for this scalar valued function was the square root of x squared plus y squared plus z squared. Then this is really something to the power of 1/2. And then when you take the derivative, you're going to move that 1/2 out front, end up with the square root of everything in the denominator, and then the chain rule is going to start putting like a 2x if I did the x partial derivative, and then these 2's would cancel and you'd end up with exactly this expression. Okay, one more of these going in the regular direction. What I want you to observe about example C is that I have 3 parts of this function, and the first part has all 3 variables in this. So I'm thinking of this as like some function of x and y and z. And then this part only has the y's and z's in it. So I'm thinking of this as just being a function. I'm going to call it h. G for function, F for function, G for function, H for function. And then the last function here only has z's in it. Now, since these two pieces don't have any x's in them, then they're entirely lost in the first coordinate. Since they're just constants with respect to x, they just completely go away, and all of that information is deleted when you take the x partial derivative. So pretend you couldn't see this for a second. When I see these two terms in the x-coordinate and the y-coordinate, this really looks to me like it came from taking the derivative of something that had a x and a y and a z term in it. And now that there's this new part in the y-coordinate, since no cosines or sines or anything are present in the x-coordinate, that makes me think that this came from some kind of sine function that had no x's in it. And you can see it did right there. This is some kind of sine function and it had no x's in it. I just want to be clear, in this middle term, this is the y partial derivative. So y is the variable and z is a constant. So this is z is here from the chain rule. Okay, again, pretend you couldn't see the original scalar function that I was using. So I kind of like to imagine myself walking down these coordinates and looking up and seeing what information I get. When I see the first piece of information, that makes me think that there must have been some function that had x and y and z. And then this guy makes me think that I also must have had some function that had only y and z in it. And then this piece of information is actually just consistent with the piece of information that I got from the first coordinate. And then here, again, I'm seeing something that has x's and y's and z's in it. So that's all consistent with this. Now this, to me, looks like a function that has only y and z in it, so that's consistent with this. And then this guy right here is all new, so this means I must have had some function that had just z on the end in order to produce something in the z coordinate that only had z's in it. And that's exactly the form of this function. Something with x's and y's and z's, something with y's and z's, and something with just z's. I want to make you aware of this historical figure, Pierre-Simon Laplace. He was a polymath and a fantastic scientist and mathematician and physicist and politician. A lot of the math that engineering and mathematical physics uses can trace its origin back to Laplace. My experience is that this is the most popular way for students to find potential functions, is really just stare at it until the answer comes to them. I think that you can do this too with some simple cases. So let me just write down some simple vector valued functions and see if you can try solution by staring. Okay, 10 hours of the Jeopardy theme song. So I'm just going to let the whole video play. Okay, are you ready for the reveal? Here it is. This was the potential function that I was thinking of, and I took a bunch of partial derivatives, and I got these signs. This makes sense because the derivative of negative cosine is sine, and then if I took the x, if x was the variable, and these two were constants, then they would come out front during the chain rule. This guy's not staring intently enough. There we go. Okay, when I look at this one, I see that in both the y-coordinate and the z-coordinate, there isn't any x's. So that makes me think that I had some kind of like function with just x's in it out front, and then some other kind of function that had just y's and z's in it, and they were added together. That's what I started with. And then the x derivative, all of this would just go away. Then in the y and z derivatives, this part would go away. And then this z and this y right here is produced by the chain rule. If I have something, for example, in the y coordinate that has like a z, just a lonely z in it, that makes me think that I had something like e to the yz, because then when I took the y partial derivative, this z would come out front from the chain rule. If it doesn't work, just stare harder. The next method is really, my experience has been, it's not popular with students, and usually students just default to the solution by staring method. But sometimes the problems just get a little bit too complicated, and there's just a little bit too many moving parts. And if that's the case, then you're going to use the zigzag method. That involves starting with one of the coordinates. I'm going to choose x in this case, and doing a series of antiderivatives and then partial derivatives and then antiderivatives and then partial derivatives, and comparing what you get at each stage to what you know the answer is supposed to be. Usually when you take antiderivatives, you have to put an arbitrary constant on the end. So if I'm given that the partial x derivative of some function was something like 3x squared y, then that makes me think that the original function was x cubed y plus some arbitrary constant. But let's think about this, because when you take an x partial derivative, numbers aren't the only thing that's constant. If you take an x partial derivative, then that process involves y being constant and z being constant. In fact, if f was x cubed y plus y to the power of 100 times the square root of z plus 3, when you take an x partial derivative, all of this is just gone. Or it could have been x cubed y plus maybe the cosine of the natural log of z minus 13. If you took the x partial derivative, then this whole cosine doesn't have any x's in it, so an x partial derivative, this whole thing would be gone as well. So actually this constant c, it isn't just a constant in this, it actually could be a function of y and z alone. So I'm going to think of that as some kind of mystery function, and the way that we're going to write this is f of x, y, z, and then at the end, instead of an arbitrary constant being put on, we're going to tack on an arbitrary function. And the only thing that we know about this function is that it doesn't have any x's in it, because there was nothing present in the x partial derivative. Okay, so here's our vector valued function to work with. We're looking for some little f, and this is supposed to be f sub x, and this whole thing right here is supposed to be f sub y, and this whole thing right here is supposed to be f sub z. So the first thing is, to me, this looks like a natural logarithm, and then there's the chain rule from this x squared. And then the issue is I want to put a plus c on the end because I took an antiderivative, but that doesn't make sense in this context because I need to put a mystery function on the end. In fact, anything that had only y's and z's in it would have been eliminated when I took the x partial derivative. So what I need here is some function of just y and z alone. So to figure out what this mystery function is, I need to use the other pieces of information. So the next piece of information that I'm going to use is the middle term in this vector valued function. That's supposed to be the y partial derivative of the potential function. And here I'm supposed to have the potential function. So let me take the y partial derivative of my answer and see what I get. So g is a mystery function of y and z alone, and now I'm taking the y partial derivative, so this needs to be g sub y. In order for little f to be the potential, then whatever the y partial derivative of f is, it must match with the middle coordinate of this vector valued function. And so far it's matching pretty good. This piece right here matches with this middle term in the vector valued function. And then I sort of have this kind of mystery piece that's tacked on the end. So that must be my mystery function of y and z alone. So if the y partial derivative of my mystery function is supposed to be negative 2yz, then I can take a y antiderivative of this, and I know that the mystery function must have been negative y squared z. And I want to put some arbitrary constant on the end, except anything that had just z's in it would have gone away. So I need to have another mystery function. This time the mystery function is going to only have z's in it. So I've worked out what the mystery function must have been from my first step. So now I'm going to take that and plug it back in for the mystery function in my original guess for what the potential must have been. Okay, now I'm one step closer to figuring out what this potential function was. I haven't used the information in the z coordinate. So if this is supposed to be the potential function, I need to somehow compare it to the information that I have in the z coordinate. And what's supposed to go there is the z partial derivative. So what I can do is take the z partial derivative of my potential function and compare it to what's in the z coordinate. Okay, so when I'm taking the z partial derivative, all of this natural log of x squared plus y squared is going to go away. Then when I take the z partial derivative of this, y squared is going to be a constant, and this is z to the power of 1, so I just get negative y squared. And now this mystery function is just a function of a single variable, so I'm not actually taking a partial derivative of this, so I can just write h prime of z, because this is just an ordinary derivative. Okay, so let's compare that to what goes in the z coordinate. So this is given information. This is the z partial derivative of the function. So let's just see if it's matching. So it looks like this piece right here matches perfectly with that. So h prime of z must have been 7e to the z. So now I can just do a regular old antiderivative. So h of z must have been 7e to the z plus. And now there's no more constants left that could have gotten deleted. There's no more variables left in this. So now finally I can just put a regular old constant on the end. Okay, we've done it. This is it. We've got the final answer. Now I can just take this h and plug it back in for what h must have been in the potential function. Okay, so this is the information that I got from taking the x antiderivative. And there's the information I got from the mystery function g. And then this is it. Here's the information I got from the mystery function h. So that's the answer. Whew, okay, we did it. That was easy. No problem, right? Okay, one more quick example. Let's try to use the zigzag method on this problem. Look, if this is supposed to be the x partial derivative and this is supposed to be the y partial derivative, then you're just going nowhere. It is not possible because this vector valued function isn't conservative because it doesn't pass the mixed partial theorem. So you got to be careful. The fundamental theorem of line integrals is awesome and it really makes problems easier, but you can see from this, if you just start making up random formulas and sticking them in the coordinates of a vector valued function, then you're probably not going to produce a function that has a potential. One easy way to spot that a math textbook is giving you a problem where they expect you to use the fundamental theorem of line integrals is if they don't describe a path remember that line integrals of conservative functions or line integrals of exact differential forms are independent of path. So if you're ever asked to calculate a line integral like this one, and there's no path, then that's a big hint that differential form is exact, or that the vector valued function is a conservative function, and so you should just start looking for a potential. And I got 18, so if you can ever use the fundamental theorem of line integrals, it's so much better. I mean, I think you can see that really this problem just, took no time at all. So yeah, thanks, fundamental theorem of line integrals. It always feels strange from a student point of view to learn a math technique that takes really hard problems and makes them really easy, because the examples are so much more simple than the theory. Hopefully I've impressed upon you that the main point of this is to make a connection between a very special kind of vector valued function, conservative functions, and the interpretation of that in the real world. I think that takeaway is a lot more important than, this really easy kind of process of pushing the symbols around on the page in order to calculate line integrals. If you are having difficulty calculating line integrals, then you should just watch some SpongeBob. That it helps me.